Hello all, good evening. Am I audible? And yeah, I hope this slides are
Yeah,
saved.
yeah, ma'am, audible.
Thank you. So yeah, this is the week 4 summary for the probability and statistical inference course. So this week we'll be looking more about the more in detail of the maths and the distribution functions related to probability theories. So let's get started with this week's lecture. So first before that, let's look at independent events. So something in continuity with what we saw in the previous weeks. So two events are independent if the occurrence or non-occurrence of one event does not affect the outcome of the other event. So yeah, events A and B are independent if the probability of event A has no effect on the probability of event B. So I'll just quickly go through these because yeah, it's just easily understandable if you just go through the slides. So yeah, if two events A and B are independent, their complement events, the A complement A bar and AB complement, they are also independent. So for example, let one event be the event that you get a king out of a selected card. And the other event be that the event is a heart. So if you draw a king from the deck of the cards, the event hedge does not depend on whether you get a king or not. So that's why these two events here are independent. The probability of drawing a heart still remains unchanged, irrespective of what happens in the event K in the previous event. So that's why these two events are called independent events. So yeah, let's go to the next topic, which is how to compute probability using R. So when you want to compute probability with R, you can use different approaches to compute the probability. You could compute probability in terms of the relative frequencies, and a logical operator can be used for finding relative frequencies, like logical operators like and or. Like in case you want to find A intersection B, you have to use the logical operator and when you want to find the probability of A union B, you have to use the logical operators or, which is the pipe symbols. So that's one way you could compute the probability. And also a function can be written to compute different combinations of the probabilities. So let's see some examples. So yeah, like here in this example, suppose a fair dice is rolled and its outcome is the number of points, the number of dots on the upper surface of the dice. So when the number on the dice is just one dot, the event is one. And when you have two dots, it's two, and so on, like when you have six dots. So the sample space would be numbers 1 to 6. And you want to compute the probabilities of occurrences of each of these numbers. So you know that for each of these values, the probability is 1/6. So 1 divided by the total number of outcomes. So in other words, you could say that it's the relative frequencies of one, like how many times you get the number 1 compared to the total number of expected outcomes. So here, when you repeat the experiment for 100 times, you want to count the number of ones that you get. So for example, you roll the dice 100 times. So the first time you get number 2, next time you get 6, next time you get 1, next time you get 1, next time you get 5, and so on for 100 times. So let's say you get 15, in here in this case, you want to calculate the number of twos. So you get 15 twos out of the 100 rolls. So here the probability of occurrence of a 2 would be the relative frequency, which is like 15/100. So this can be used as a way to calculate the probability with R. And yeah, let's just see how you can do this. So yeah, we have already seen that the sample function is used for random sampling. Like you would specify the numbers 1 to 100. And let's say the number of times you conduct an experiment. Like here, let's say 10 times. So you just want to draw 10 numbers. Like y- like for example, here in this case, the roll of a dice, you might get numbers 1 to 6. but you conduct 10, you roll the dice 10 times. So you'll have 10 values ranging between the numbers 1 to 6. So you want to generate this random sample. So for that, you use this function sample. Like what are the numbers that you want to be randomly sampled? So in this case, it's 1 to 6. And how many times? 10 times. So if you want 100 times, you do 100. If you want 1000, you put 1000. And replace is equal to true, because like you roll the dice 10 times and you could have like the same, the repetitive numbers. So like you can have 1, comma 1, comma 3, comma 5, comma 6, comma 2 or anything. And like a same number can repeat more than once. So that's why you write replace equal to 2. So this would give you random sampling. So these are the randomly sampled numbers. And the next, what you want to do, you want to compute the probability of occurrence of 2. So what you should do, you have to count how many times here in this random sample has 2 occurred. So like when you look at it manually, you can count that there are 3 2s. So it's 3 by 10. But when you have like numerous values, you cannot just manually look at the numbers and count them. So how do you do that with R? You use a you can either like compute it using length. So this is the object. Dice 10 is your randomly sampled object. It has all these digits, 6 to 1 and all this. It has like 10 digits here. So if you do the length of dice 10, the length would be 10. Now you just want to calculate how many twos are there, the length of the number of twos. So you have to subset this data frame. So you want to subset, like you want the value of dice 10 is equal to 2. And you want to subset the data frame accordingly. So this is the format for subsetting a data frame. And you want to calculate the length of this. And when you write this, you get 3. So now the probability of 2 would be length of this divided by length of this. So which is 3 by 10 is equal to 0 0.3. So 30% chances that you might get number 2 when you roll the dice 10 times. So we could like I could just share, I could demonstrate this in R if that makes it better. Let me just reshare my screen. So this is R Studio. So first, we just need to randomly sample them. So let's do a random sampling for 1000 experiments, like 1000 times. We randomly sample this. Let's make a dice 1000. If you look at dice 1000, it'll have like 1000 values, 1000 values of numbers 1 to 6. Now let's count the occurrence of 2. So first, now what is the length of dice 1000 is 1000. Is there any WhatsApp group to study this course? No, there is no WhatsApp calls. We would just upload these recordings and we'd share the notes on a shared Google Drive and we will upload it on YouTube. So yeah, otherwise there's no other platform. But yeah, that would be a good idea. Yeah, so just coming back to this. So we did random sampling, we found the length of the original sample. Now we want to count how many twos are there. So we have to first subset our data frame. So first dice 1000. You want only the values of dice 1000 which are 2. And you want to find the length of it. So it's 174. So the probability of the dice, probability of 2 would be this length of 2 divided by total length of the dice. So P2 is 1, so 0.174. So there's 17% chance that you would get 2 when you roll the dice 1000 times. So this is closer to 0.16. So like we know that the defined probability of the dice roll is 1 by 6. So 1 by 6 is something close to 1.666, close to 1.7. So yeah, when we learned before, so when it converges to infinity, when the number of experiments converge to infinity, your relative frequency becomes a number which is closer to this probability. So as you can see, like when you roll the dice 1000 times, your value is much closer to 0.16. So this is one way to calculate with R based on this relative frequency, the length occurrence. And now let's say you want to compute the probability of A union B. So let's say you want to calculate the number of occurrences of 2 or 6. So A union B is OR. So you have to use the logical operator OR. So let's first compute the length of A union B. So length of dice 1000 is equal to 2, dice 1000 is equal to 6. So this pipe symbol here means OR. So A union B. Union is OR. So this pipe symbol means union. If you put an ampersand symbol and symbol, it is intersection. So we just want union here. So we are using pipe. So it's 336. So if you do 336 divided by 1000, you'll get your probability for A union B. And then, yeah, like I said, if you want A intersection B, you do A and. So let's see, like getting both 2 and 6. Getting 2 and 6 on a dice is impossible. So when you roll a dice, you just get either 2 or 6. So when you do and, you should get a value 0. So yeah, as you can see, you can expect a 0 here. But for when you want to do and, your question would be different. So maybe like when you roll 2 dice and the sum of the digits on the dice is equal to 2, something like that. So like here, for example, here you toss a coin and 1 indicates head, 0 indicates tail. So here random sampling, you just do 0 and 1 instead of numbers 1 to 6 on a dice, because 0 and 1 is the sample space here. And you conduct just one experiment, one toss. So you write size is equal to 1. So you can see, like, you can get either 0 or 1. So, but here, yeah, so that topic is over. Like how to compute probability with R, we're done with that. Now the next topic that we're looking at is random variables. So now what are random variables here? Well, okay, let me reshare my screen so that. So now there's another term called random variables. So now let's just quickly see what random variables mean. So like some concepts are required to draw statistical conclusions from a sample space. So we know that the salary of a sample of 100 students graduating in statistics. So yeah, if you want to know something, we need to compute numbers. You can't do anything with terminology. Like let's get back to our tossing a coin example. So when you want to compute statistics, you need numbers like 0, 1, and 2. Like when you have these values like head and tail, you cannot the like feed this into your algorithm computationally. Your algorithm cannot compute what is head and what is tail. So you need to assign these head and tail to some numerical value. So these values to which you assign some outcomes are called random variables. You call them random variables because these are just random numbers. You can also assign these anything you want. You could also like consider head is like 10 or tail like the 100. So it's just up to you. You can assign some random number to indicate a particular outcome. So that's why you call these random variables. So here in this example, you consider one, like if you get a head, you assign a value of 1. And if you get a tail, you assign a value of 0. So these 1 and 0 here are random variables. So let x be the function. So omega is your sample space. So the function of the sample space is such that x is 1, x of omega is 1 if omega is head, and x of omega is 0 if omega is tail. So the sample space of real numbers, the actual sample space is head or tail. But since you have assigned these to some values, the sample space now is 0, comma 1. So x, so this is x1 and this is x2. So this x here is called a random variable. And it's called random, again, it's also random because the outcome is random. Like you don't know what the outcome would be unless your experiment is completed. So in any random experiment, we're interested in the value of the numerical quantity determined by the result, as we said, like because that would be used to compute by the machine. And you're not interested in the details of the experiment. So these quantities of interest that are determined by the result of the experiment are known as random variables. So now we also know the probability of a random variable. So like you know the probability of a head and the probability of tail. So you can assign the probability to the random variable as well. So since the value for random variable is determined by the outcome of the experiment, you can assign these probabilities of its possible values. For example, probability of head is 1 by 2. So the probability of getting a random variable of 0 is also 1 by 2 here. And the probability of getting a random variable 1 is also 1 by 2. So X is a random variable which collects the possible outcomes of a random experiment and captures the uncertainty associated with them. So this random variable is just associated with either head or a tail. So again, like when you roll a dice, let's consider the sample space to be the numbers on the dice. When added, you get a sum of 7. So your sample space would be 1, 6, 2, 5, 3, 4, and all these. So here your random variables would be as follows. So let your experiment be like your sample space is an experiment where you record the sum of the dots on a dice. So in that case, your sum can be 2, 3, 4, up to 12 because like you cannot have anything below 2 because when you roll a dice, your minimum value you get is 1 plus 1 and your maximum you get is 6 plus 6. So which is 12. So a sum of 2, like when you get 1, 1, the random variable is 2. And when you get a sum of 3, so here your sample space can be 1, 2 or 2, 1. So here your random variable is 3. And let's say when you get all these 6, 1, 1, 6, 5, 2, 2, 5, 4, 3, 3, 4, your random variable is 7. So here you assign just like 10 random variables that indicate all these 36 different outcomes. So in other words, the random variable x can take on any integral value between 2 and 12. So when you look at this, it can take any value between 2 and 12. And the probability that it takes on each value is obtained. So you can define this as a function. Let's say you can define this as some function, and the data points are 2 to 12. So you can define this curve as something as a function. And you can, like from that definition of that function, you can apply whatever value you want, and you can obtain the probability using that small mathematical notation. So this is how you define it. So this is the probability of your sample space. So this is defined as an integration, like a sum, an integral between 2 to 12, and the probability of x is equal to I. So this I could be anything between like 2 to 12. So like when you add all the probabilities of all these, you would get a total of 1. So this one here denotes your function. So yeah, so like in convention, random variable, like probability of random variable, you denote this by x. So a random variable is denoted by x. And all the outcomes of this, like for example, uh, all the outcomes within a random variable is denoted by small x, x2. So for example, you're calculating the height of students in a class. So x is equal to height of students. So you're assigning a random variable x to denote height. So all the values, the events in this sample space are x1, x2, x3, and so on. So yeah, the height could be 160 centimeters, 158 centimeters, 175 centimeters. So all these are denoted by small x. So the random variable now can further be classified into two types. So it can be either continuous or discrete. So now let's see what a continuous random variable means and what a discrete random variable means. So discrete is when your sample space is countable. It's a countable set of numbers. Like you have to count it like 1, 2, 3, 4, 5, and so on, like 30, 100. Any such whole numbers which you can count are discrete. And in case you are measuring, like for example, you're counting the number of students, like in a class of students, you want to count the number of girls and you want to count the number of boys. So this has to be a discrete value. It can be like 2 girls, 5 boys, 6 boys, 10 girls, and so on. It has to be a whole number. Yeah, let me just. Please mute yourselves, everybody. Yeah. Okay, yeah, getting back to it. So yeah, when you count the number of girls and boys, it has to be a whole number. You can't say there's like 2.5 girls, there's 2.5, 5.5 boys, 5.2 boys. You can't say something like that. So such whole number countable values are discrete. And on the other hand, when you measure like for example, you're taking a measurement of something. You're measuring somebody's height. So height can be 168.4 centimeter, or it can be 170.1, or it can also be 150.55. So these such small measurements, which can be like on a continuous scale. So you can denote this by 4, 5, 6, like any number ranging between 168 to 178. And it can be any decimal value. So such values are called continuous values. So when you're dealing with such random variables, they are called continuous random variables. So these are just examples that tell you, like discrete variable, again, like the number of times you make a call. So you make a call 5 times or 2 times. So these are whole numbers. So it's a discrete random variable. The number of machines that function and the number of machines that are not functional. These are also like whole numbers. So these are discrete random variables. And on like continuous random variables, suppose a dimensional length is measured, such as vibrations, temperature fluctuations, calibrations, uh, raw material changes, like length, and all these continuous numbers are continuous random variables. Like continuous random, they exist on a continuum. Like it can be like minute changes of the values. Yeah, the same thing. So now let's define functions, the probability functions, to like summarize these uh, random variables. So we are choosing some event A. So this event ranges between values minus infinity and x. So x belongs to R, which is like superset, and A is a subset of R. So probability of this event. So probability that x belongs to A, probability that your random variables belongs to your your sample space. So probability of x belongs to A can be calculated as probability of x belongs to this interval, minus infinity to x. So you could also define it like x is greater than minus infinity and x is lesser than or equal to this x. So finally you compute probability of x such that it is lesser than or equal to this given value. So this is your basic like function. So probability that x belongs to A is equal to probability of x such that it is less than or equal to small x. So this is the definition of cumulative distributive function, which you abbreviate as CDF. So it's called cumulative distribution function. So you learn about this further, you'll understand it better. So now let's get into the maths of this cumulative distribution functions and the probability density functions that arise from these. So we already defined a cumulative distribution function, like in the previous slide, like probability that x belongs to A is equal to probability of x less than equal to x. So it's denoted by f of x, function of x. So the cumulative distribution function, or just simply the distribution function, it can be called CDF or just DF, like distribution function. So the CDF of a random variable x for any real number small x is denoted by this function like we saw. And f of x is the probability that the random variable x takes on a value that is less than or equal to x. So this is just the definition of a cumulative distribution function. So these are some mathematical properties of the cumulative distribution function. So f of x is a monotonically non-decreasing function. Like, well, let's say you define y is equal to x square. So you know that if you increase the value of x, the value of y also increases. If x is equal to 1, y is also equal to 1. If x is equal to 2, y is equal to 4. If x is equal to 3, y is equal to 9. So if x increases, y also increases. So this is also similar. So your f of x, the probability, the CDF, the function of x increases if your value of x also increases. And also like, yeah, smaller f of x1 is always smaller than f of x2. And also the lower limit of f of x is 0. And the upper limit of f of x is 1. Just like, the probabilities range from between 0 to 1. And it's also continuous. And all of x, so everything ranges between 0 to 1. These are the basic properties, like they're non-decreasing and they range between 0 to 1. This is the lower limit and this is the upper limit. So these are just some formula you need to remember, like how do you compute the function for given interval. So all the probability of x can be computed in terms of its distribution functions. Suppose you want to compute probability of x greater than a and less than equal to b. So this would be function of b minus function of a, like f of a, the CDF, cumulative distribution function. So this is similar to like you want to calculate the probability of somebody's height falls between 150 and 175. So what you do here, you do 175 minus 150 or whatever function it is. Like, so this is something you have to remember. And similarly, like if you want to compute the probability for x is greater than or equal to a and greater than less than a, you do f of b minus f of a. Like you will look at these calculations further. So the CDF is useful in obtaining the probabilities related to the occurrence of random events. So it's helpful when you want to calculate the probability. So this is just one example here. So suppose the random variable x has the distribution function. So if x is greater than 0, if it's anything like 1, 2, 3, or any number greater than 0, it follows a function 1 minus exponential of minus x square. So it's e power minus x square. And if it is less than, if x is less than or equal to 0, the function is just 0. So the probability that x is greater than 1. So you want to calculate probability of x greater than 1. Probability of x greater than 1 is equal to probability of 1 minus probability of x less than or equal to 1. So by definition, this is what you have. So this would be just 1 minus f of 1. So when x is, so here x is equal to 1. So x is equal to 1 is, that means x is greater than 0. So here you apply 1 minus f of x. F of 1 here is again 1 minus e power minus x square. So solving for this, you get exponential of minus 1. So this is just like an example of this particular function of how you solve this. Let's look at much simpler ones in the next slides. So yeah, so a random variable x is said to be continuous if there's a function f of x, such as for all x belongs to R, f of x, the function follows an integral like this. F of x is equal to minus infinity to a given value of x, f of t dt. So here this capital F of x is your CDF and the small f of s is your probability density function. So it's your probability function of x. And also like the integral of PDF gives you CDF. And also the differential of CDF would give you PDF. That's what this one means here. So again, we're just like defining it. The probability density of function of continuous random variables. Like all the it will be greater than or equal to 0 and it ranges between minus this, like the summation of all the values in the given sample space the probability of the summation of the probabilities of all them would be 1. Which is again the same thing. So we just saw the definitions of when you want to calculate a less than or equal to x, x greater than equal to a less than equal to b, you do probability of b minus like f of b minus f of a. So that's what they've done here. It's just another example. So here we also defined this integral. So what do you mean here by integral? Integral is nothing but you must have come across the term area under a curve. So like any data points you collect or anything that I do, it follows a certain distribution functions. So here let's just consider this kind of a distribution. It's called like a normal distribution. So here it's like 0. This is your minus infinity. This is your infinity. So we solve the part. So let's say you want to calculate the probability of the values lying between 2 and 3. So what do you do now? So integral of minus infinity to plus infinity is the whole area of this under this curve here. But you just want the specific area between these numbers. So first you'll have to calculate the function at f of 3. So this would give you the area here. And then you calculate f of 2. So this would give you all these values here. So when you subtract this f of 3 minus f of 2, you will get the value ranging between 2 and 3. So this is the basic idea of the CDF and how you could compute the probability at any given point of this curve. So here's one example. So they have defined a function f of x is equal to exponential of minus x if x is greater than or equal to 0, and f of x is 0 if x is less than 0. So when you plot this on a graph, it will look like a curve like this. And here you want to calculate the area between A and B. So you just want to calculate the shaded area here. So what do? You calculate probability like the function at B minus the function at A. That would give you this shaded area. So in other words, it's just like multiple histograms, like small data points over here. And then you have its center value and you just connect all these values and you get a distribution curve. So it's just like an interval. So for each interval in this histogram, the area of the bar, each bar, it equals to the relative frequency of the measurements in that particular interval. So let's consider an example here. So we consider a random variable, which is for waiting time of the train. Waiting for train, the time. The train arrives every 20 minutes. So here your interval will range between 0 to 20. Because like you reach a station and the train has already departed, you have to wait for 20 more minutes. But yeah, you reach like maybe 10 minutes until your train, like you have to wait for 10 minutes. So your interval ranges between 0 to 20. So here they define a function f of x is some value k for this interval 0 to 20 and then 0 otherwise. So this k is here is constant. So how do you calculate the probability now? So here this is the definition. So we know that the summation, the whole interval between 0 to 20 would be 1. The probability of this all entire integral of this whole interval would be 1. So now we use this f of x dx. So we know that f of x is the probability density function. So it is given that this f of x here is your k. So you just have k in place of f of x and dx 0 to 20. And because k is a constant, this is 1. So k is just a constant. You just directly apply these values here. So you'll get 20k minus 0k is equal to 1. 0k is 0. So 20k is equal to 1. K is equal to 1 by 20. So now you rewrite your function like this. So f of x is equal to 1 by 20 if x is between 0 to 20 and f of x is 0 otherwise. Now you write the CDF. So CDF is f of x 0 to x f of t dt, which is f of x dx. You can also write it that way. So in 0 to x. Now we just calculated that this is 1 by 20. So 1 by 20 dt. So now when you apply this, so 1 by 20 is a constant. So it would just be something like x dt. So it would be like x by 20 minus x by 0. Oh, sorry, 0 by 20. So this term is 0. So your cumulative density cumulative distribution function f of x is equal to x by 20 here in this case. So now we are interested in calculating the probability of waiting time between 15 and 20 minutes. So you could derive this from this expression that we calculated. So we know that like probability of a b is equal to f of b minus f of a. So here f of 20 minus f of 15. So f of x is equal to the CDF f of x is equal to x by 20. So here instead of x you apply 20 here, and here instead of x you apply 15. So 20 minus 15 is equal to 5 by 20. It's equal to 1 by 4. So you have to, like, this is the probability. So 25% chances that your waiting time is 15 to 20 minutes. So just with this CDF x by 20, you could calculate the probability of like any waiting time between 0 to 20. So if your waiting time, you want to know what is the probability of your waiting time, that is 5 to 10, you could apply the same thing. So it would just be 10 divided by 20 minus 5 divided by 20. So yeah, it just simplifies your whole thing. So this was in case of discrete random variables. So all this, sorry. So this was in case of continuous random variables. And now let's look at discrete random variables. We know that discrete random variables, these are like whole round numbers. So let x denote the random variable to be the number of defective components of a device. Yeah, all these are just examples. We don't need to know this. Okay, let's just quickly go through this example. So yeah, it's just again like you denote this experiment of tossing a coin, getting a head is 1, getting a tail is 0. So this cannot be anything like 1.5, 1.2, because yeah, that's why this is called a discrete function. In our previous example, like you can also calculate your waiting time for 7.5 minutes, 5.5 minutes, 12.3 minutes. Like you could just apply 12.3 by 20 minus 5.5 by 20. So that was a continuous function. This is the discrete one. So you have defined the function here. You could also define the function like for events, there are number of heads. So you toss 2 coins. So in that case, you can get 0 heads or 2 heads or 1 head. So you can define the function like this. And you can also assign the probability to them. So probability of getting a 0 here is 1 by 4. Probability of getting this is equal to 2 by 4 is equal to 1 by 2. Probability of getting 2 heads is also equal to 1 by 4. So yeah, this is just like the same definitions and examples. Mm. So now for continuous random variable, you had something called probability density function. But now in case of discrete random variables, you would have something called probability mass function. So this function, the distribution here, is specified by a list of all possible values along with the probability of each outcome. So it gives you what the value and the probability of getting that particular value. So it is convenient to express the probability in terms of this formula. So again, like this is how you define a probability mass function. It ranges between 0 to 1, and you denote it by the summation of like something like 0 to x, 1 to k, and all this is 1. And here the cumulative density function, the CDF of a discrete random variable is always a step function. So we'll see what that is. In our for a continuous variable, it was like a continuum. It was a continuous function or something like this. But here, for this, you'll have something like a step function. And these are the formula you have to know how to compute them. So these are just some examples of how you define these functions. Like again, you like define a CDF and PMF for the number value on a dice. And its associated probability here is 1 by 6. If x is equal to 1, 1 by 6 if x is equal to, and so on. So you denote this by this interval given here. So like your CDF, the probability CDF will look like something like this. So when you don't roll anything, it's just 0. Your step will be here. And then when you get a 1, your step jumps over here. So on. So now when you want to calculate the probability of getting probability that your x is between 3 and 5. So it would just be, I'm sorry, yeah, 5 is here. So this is 5 by 6 minus, sorry, minus 3 by 6. So this will give the probability that your number is between 3 and 5. Mm, And then finally, we'll be talking about expectation of variables. So we saw CDF and PDF and PMF. We saw about random variables. And now we'll learn about expectation of random variables. So what is expectation? So when you toss a coin, you expect either a head or a tail. So expectation is when you decide that you get some reward when you get a particular outcome. For example, if you get a head, the probability of getting a head is 1 by 2. Probability of getting a tail is also 1 by 2. But if you get a head, your reward is rupees 2. If you get a tail, your reward is rupees 4. So what is the expectation of the reward, average reward here? So you would do something like 1 by 2 multiplied by 2 plus 1 by 2 multiplied by 4. 1 plus 2, 3. So yeah, your average expected reward here is rupees 3. So similarly, like for the dice rolls, you get 1 rupee if you get a number 1. If you get 6 rupees if you roll a number 6. So the average expected reward money is, you just multiply all these values. So 1 into 1 by 6, 2 into 1 by 6, 3, and so on. So your average reward is 3.5. So yeah, so that's how we mathematically chats. For some of the questions of the given options are incorrect. I am worried about the evaluation loss of marks. Can you just let me know what question numbers these are? Yeah, you just let me know that in the chat box, and yeah, let me just finish this. Okay, so how do you mathematically define the expectation of a continuous random variable? So it is denoted by expectation of g of x, like expectation of x, whatever you want. So it is nothing but the probability density function or the probability mass function. So basically the probability function multiplied by g of x. So g of x is a real valued function of x. It's a function of x. So you just denote this by the summation integral of g of x into f of x dx. So let's just understand this further. So yeah, g of x is your actual value, and p is the probability of your value. So the summation of all these gives you the expectation, just similar to what we saw here. So this one here is f of x. These values here, these are g of x. And when you have a constant number, it comes out of your equation. Like e of x could be some function, and e of ax is just a multiplied by e of x. That's what this slide summarizes. So yeah, let's look at the example of the waiting time of the bus again. We just computed the probability density function, that if you're waiting for any waiting time between 0 to 20, your probability density function is 1 by 20 and 0 otherwise. So yeah, how do you calculate the expectation, the average expected wait time, something like that? So you don't, so instead of minus infinity to plus infinity, you break down the equation here, because the range you're interested in is 0 to 20. So you break it down as minus infinity to 0, and then 0 to 20 x f of x dx, and then 20 to infinity x dx. So all these are 0. So based on this previous function that we defined here, if it's anything outside this given range, it is all 0. So these two terms become 0 here. So you're just interested in integral of 0 to 20 x f of x dx. So you have 0 to 20 x, f of x is 1 by 20. Like f of x is equal to 1 by 20. 1 by 20 dx. So 1 by 20 comes out of the equation now, 0 to 20 x dx. So this, like when you integrate x, it gives you x square by 2. 0 to 20, and this 1 by 20 is already outside. So now how do you write this? So yeah, it has to be the sum of all these values. So it becomes x square by 40. Just a second. So when you apply all these values and calculate the sum, you average, you get a value of 10. So the average waiting time for the train is 10 minutes. I'm sorry, you don't take the integral here. So it's just like the summation of x into the probability function. So that's what your expectation is. So it's like, So you have x by 20, 0 to 20. So you just have to add like 0 to 20 plus 1 by 20 plus 2 by 20 plus and so on until 20 by 20. So if you solve for this, you get a value of 10. So the expectation of x here is 10. And this is how you calculate it with R. So basically, like for average value, you use the function called mean. So mean of all these numbers gives you the average value, the expectation. So now let's try to solve some questions from previous year that will help you to solve this week's assignment as well. Can you see my screen? Okay. See? Yeah, I hope these are seen. So these are some questions from previous year's question paper. Let's solve these one by one. And okay, so the following circuit operates only if there's a path of functional device. Oh, just a second. Okay. So the following circuit operates if there's a path of functional devices from left to right. The probability that device 1 functions is 0.6, and the probability that device 2 functions is 0.5. Assume that the devices fail independently. So what is the probability that the circuit operates? So let's consider probability of device 1 is equal to 0.6. So this is already given. Probability of device 2 is equal to 0.5. So because they are independent events, the probability that both device 1 and device 2 function is given by product of their individual probabilities. So we need to calculate probability that that the circuit operates. So the circuit operates is like both these, they operate. So the probabilities of independent events would be just probability of A into probability of B. So in this case, probability of D1 into probability of D2, 0.6 into 0.5 is equal to 0.30. That answers your question. So this is because these are independent events. So yeah, and the next one is find the probability at x is equal to -3 and x is equal to 3 from the CDF given here. Okay. So for x is equal to -3, so when x is lesser than or equal to -3, your value is 0.3. So the probability at x is equal to -3 is equal to 0.3. And now your probability at x is equal to 3, 3 here is equal to, there's nothing 3. So you want to calculate this. So you do 1 minus, like probability of x greater than equal to 3 minus, which is 1 minus probability of x less than 3, 0.8. So you get 0.2. So this is your answer to this question. So this next question is, in a shoe factory, suppose 50 shoes out of 850 shoes manufactured every day are defective. So these are defective shoes. 2 shoes are selected at random without replacement from the batch. Let the random variable x equal to the number of defective shoes in the sample. What is the cumulative distribution function of X? So you define the cumulative distribution function for 0, 1, and 2 because you just pick two shoes at random. And when you pick two shoes at random, the number of defective shoes can be either 0 or one shoe can be defective or two shoes can be defective. So you need to define your cumulative CDF at 0, 1, and 2. So let X is equal to 0 be like 0 number of defective shoes. 1 is equal to 1 defective shoe. X is equal to 2. Both shoes are defective. Both defective. So the probabilities of each value of X. The probability that if X is equal to 0 is equal to. So yeah, already you know that 50 out of 850 shoes are defective. So you have non-defective, like 800 shoes left apart from these 550. So now you pick one shoe from this. So when you pick one shoe from this, it's 799 and this becomes 849. So solving for this, you will get the value of P of X is equal to 0. And the P of X is equal to 1 would be probability of selecting one defective shoe and one non-defective shoe. So one defective shoe is equal to like 50 by 850 into again like 800 divided by 849. And probability of X is equal to 2 is equal to both shoes are defective. So you pick it from the defective lot. So 50 by 850 into 49 by 849. So solving for all these, you'll be able to calculate the values. And then next, consider an experiment of choosing a boy or a girl from a class with equal number of boys and girls. You have equal number of boys and girls. What is the cumulative distribution function of X? So random variable X denotes the number of girls. Right. Choosing a boy or a girl with equal number of boys and girls. X denotes the number of choosing girls. So you just pick one student and the X denotes the number of girls. So X can be 0. And X can be 1. So if X is anything like less than a 0, the probability is 0. So X is equal to 0 means you choose one boy. So basically the probability of choosing a boy is 1 by 2, 0.5. And choosing a girl is also 0.5. So when you choose a boy, which is 0 here, your probability of X, like choosing a girl is 0. So when you choose a girl, which is 1, the probability of choosing a girl is 1 here. And then there's an interval 0 and 1 where it can be either of these. So here you write 1. So yeah, this would be your cumulative distribution function. Well, the other things don't make any sense. So this one would mean that the probability of choosing a girl is 1, which is fine. But probability of something less than 0, probability of not choosing any student at all is 0.5. So this is wrong. We know that probability of not choosing a student is 0 because we are choosing a student. So probability of choosing a student is 1, 2. So this is wrong. This is also wrong. And yeah, this is also wrong because this one then 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, So now let's suppose x is a continuous random variable with probability density function. So here we have this function c is a constant here, c into 2x square minus 4x. If x is between 0 to 2, this is the function, and 0 otherwise. So now we need to calculate the value of the constant c and the value of the probability ranging between 0.5 and 1. So here we can define like since f of x is the probability density function, so the total area under the curve should be equal to 1. So yeah, you probability density function, you define it like f of x dx is equal to 1. So the given interval is 0 to 2. So 0 to 2 into c of 2x square minus 4x dx is equal to 1. You bring the c outside now. Yeah, you just keep the c outside now. And now what happens? So when you integrate this, 2x square. So x square would become x3 by 3 minus 4 into x integral of x dx is equal to x square by 2. So these are just some things you have to remember. So integral of x is equal to x square by 2. Integral of x square is equal to x3 by 3. Integral of x cube is equal to x4 by 4 and so on. So you just have to keep this in mind. So now this can be written as till 0 to 2 is equal to 1. So now you just substitute the values here. C of 2 by 3. Uh, uh, so instead of x, you substitute 2. 2 cube minus 4 into 2 square by 2. 2 2s are 4. Yeah, you do this. Sorry, you just keep this as such. And then so you have to do f of b minus f of a, right? So f of b is 2, a is 0. So we substituted 2 in this function already. And now we have to substitute 0. So 2 by 3 into 0 cube minus 4 by 2 into 0 square. So this whole term is anyway 0. So this whole thing would be equal to 1. So this term is already 0. So you don't worry about this. It becomes 0. So yeah, just solving for this now, you get 2 cube is 8. 8 twos are 16. So c into 16 by 3 minus 2 twos are 4. 4 twos are 8 is equal to 1. So solving this, 8 threes are 24. So you get 16 minus 24 divided by 3, 16. So this will, so c into this is equal to 1. And now solving this, you get minus 8 by 3 is equal to 1. So c is equal to, like you just move this side. C1 is equal to minus 3 by 8. So yeah, we solved these. So this is your correct answer. We have solved C now. Now what you want to do, you want to calculate the probability between 0.5 and 1. So here in this equation, we substituted 0 and 2. So instead of that, the upper limit is 1, lower limit is 0 0.5. So you had this function, right? 4x square divided by 2 minus 2x cubed divided by 3. So instead of x, you substitute 1, 1 and 0 0.5 and you solve for it, you will get 11 by 2 as given here. So that answers your question. So next question, a coin is tossed 4 times. Let f of x denote the cumulative distribution function. Then the value of f3 is. So F F3 is equal to probability of x less than equal to 3. So F3 can also be written as probability of x is equal to 0 plus probability of x is equal to 1 plus probability of x is equal to 2 plus probability of x is equal to 3 because there's less than equal to 3 here. So when you toss the coin 4 times, you'll have like 16 different outcomes, combinations. So the mm, sorry, so let me just get back to this. Yeah, I'll just get back to this because this is a different formula and yeah, we didn't cover that in this lecture. Okay, let's suppose we have suppose x is a continuous random variable with probability density function 3 exponential of minus 3x if x is greater than 0 and 0 otherwise. So now we want to calculate the CDF. So CDF, we know it is 0 to x f of t dt or f of x dx, whatever you want. But since we just have x term here, instead of writing f of x dx, like so that you don't get confused, you write f of because there's an x here in the equation already. So f of t is equal to this, it's already given. So you just substitute that 0 to x. So f of x is minus e power 3 e power minus 3 3x dx. So okay. So in general, like we just saw, when you want to integrate x, it becomes x square by 2. X square becomes x cube by 3. And similarly, if you want to integrate e power minus kx, integral of that becomes minus 1 by k e power minus kx. So here you have minus 3x to 1 minus 1 by 3 into e power minus 3x. So this one just becomes minus e power minus 3x 0 to x. So f of x is equal to, so instead of x you substitute 0 and 1. So it would be minus e power minus 3x. Again, so it will be minus e power minus 3 0 is anyway 0. So this term, this term is all 0 in any, no, e power 0 is equal to 1. So this term becomes plus 1. So rewriting it, you write 1 minus e power minus 3x. So this is your CDF. CDF, CDF, like, I'm sorry. So f of x is equal to minus 1 minus, f of x is equal to 1 minus e power minus 3x if x ranges between 0 to x. Yeah. Then the next question. So suppose x is a continuous random variable with a probability density function. So f of x is equal to 6x into 1 minus x if x ranges between 0 to 1. Sorry. You want to calculate 0 to 0.5. Yeah, so you write it like this. And now you just integrate these. 6 comes out. It is 0 to 0 0.5. X minus. Okay. Let's just keep it this way. 6x minus 6x square dx. So now integrating this, you get 6x square by 2 minus 6x cube by 3. 0 to 0.5. 2 3s are 6. 3 2s are 6. So 3x square minus 2x cube, 0 to 0.5. So now you just have to substitute 3 into 0.5 square minus 2 into 0.5 cube minus 3 into 0, it all becomes 0 anyway. So yeah, you just need to substitute these values and you will get the answer 0.5. So yeah, we could solve it. So 0.5 square is 0.25. So 3 into 0.25 minus 2 into 0.5 cube would be 0.125. So yeah. Now 3 into 0.25 would be 0.75 minus 2 into 0.125 would be 0.25. So 0.75 minus 0.25 is equal to 0.5. So now your f of x between 0 to 0.5 is 0.5. So that answers your question. So the next question, suppose a person is expecting an email at some time after 6 p.m. The person knows from experience that x, the number of hours after 6 p.m. until the message arrives, is a random variable with a probability density function. F of x is equal to 2 by 5 if x is ranges between 0 to 2.5 hours. So what is the expected amount of time after 6 p.m. until the message arrives? So the expected amount, you need to calculate expectation. Expectation of between the range 0 to 0 to 2.5. So here g of f, g of x, f of x dx. So 0 to 2.5. Your f of x is 2 by 5. Gx is x dx. So now you will get 2 by 5, x becomes x square by 2 into 0 to 2.5. These get cancelled out. So you can have x square by 5, 0 to 2.5. Now you just substitute these values. 2.5 square divided by 5 minus 0 square divided by 5. So solving these, you would get the answer to this question. So you have calculated the expectation of x. So now next question is, let's suppose a discrete random variable x has a probability mass function. So P of x is equal to 0, probability mass function 0.5. P of x is equal to 1 is equal to 0.4. P of x is equal to 2 is equal to 0.1. So you want to calculate expectation of x. So what you do here? So we saw that expectation is equal to summation of g of x into f of x. So here g of x, this is g of x, this is f of x. So you just do 0 into 0 0.5 plus 1 into 0 0.4 plus 2 into 0 0.1. So if you solve this, you get 0 into 0 by 0. 0 0.4 into 1 is 0 0.4 plus 2 into 0 0.1 is equal to 0.2. So 0.4 into 0.2 is 0.6. So E of x is equal to 0.6. Now E of x square. What is x square? You just take the squares here. Expectation of x square. So you have to do 0 square is 0. 0 into 0.5 plus 1 square into 0.4 plus 2 square into 0.1. So this is 0.4 plus 2 square is 4. 4 into 0 0.1 is 0.4. So 0.4 into 0.4 is equal to 0.8. So yeah, this answers your question. E power of x is equal to 0.6. And expectation of x is equal to 0.6. Expectation of x square is equal to 0.8. Yeah, so option B is your answer. And then next question is, suppose x is a random variable with the following probability density function. 1 by x square if it ranges between 1 to x ranges between 1 to infinity. So we have to calculate the E of 3x. So E of 3x can also be written as 3 into E of x. So yeah, let's just solve this now. Again, we know that E of x is equal to, in this case, it's 1 to infinity, g of x, f of x, dx. That's 3x. So 1 to infinity, 3x. 3x is your gx. So gx is 3x. So f of x is 1 by x square dx. So you just have 3 by x dx. So one more thing to remember is integral of 1 by x would be integral of 1 by x is equal to ln of x, and your 3 stays there. So yeah, integrating this 1 to infinity, you will get this 3 stays here. So 3 into 1 by x, integral of 1 by x is ln of x, 1 to infinity. So when you apply this, the limit tends to infinity here. So ln of infinity would be infinity. So yeah, your final, when you apply this infinity in this equation, your whole equation also becomes infinity. So the final answer, the expectation of x here is infinity. So option C here is your correct answer. So if instead of infinity, if they had given any other number like 1 to 5, you could have easily substituted 3 into ln of 5 minus 3 into ln of 1. You would have got some value. But since there's infinity, like any operation you do on an infinity is an infinity. That is your answer. And then the next question. So a lot of this. Okay. A lot of 12 cars includes 2 cars without music system. If 3 cars are chosen at random for shipment, how many cars without music system can the transporter expect to send? 2 or 12 cars, 2 cars. So yeah, the probability of getting a car without music system is equal to 2 by 12 is equal to 1 by 6. Solving for this. So that's what is given in the question. So you choose 3 cars at random now. How many so what is the expected number of cars without music system? So you can calculate this as g of x, f of x. So here f of x is equal to 1 by 6. G of x is like how many cars? You pick 3 cars in random. So g of x is equal to 3. So 3 into 1 by 6 is equal to 3, 2 are 6 is equal to 1 by 2. So that is 0 0.5. So 0 0.5 is your answer here. So these are different ways of how they can ask you. So looking at this question, you have to know that you could apply this formula, the expectation formula. So they've given the probability, f of x is given, g of x also is given here. So you could just directly multiply these both and get the answer. And then if x is the number of points rolled with a balanced die, what is expected? What is the expected value of g of x is equal to 2x square plus 1? So we know that E of x is equal to summation of g of x into probability of x is equal to x. So for each outcome, we calculate g of x and multiply by its probability and like you do sum of all possible outcomes. So here expectation of g of x is equal to, like when you roll a dice, your outcomes would be 1 to 6. So summation ranging between 1 to 6. Your function is 2x square plus 1. So multiply this into probability of x is equal to small x. So small x is 1 to 6. So, and you know that like for any uh, dice roll, any number is 1 by 6. So this one is 1 by 6 here. So your expectation is 1 by 6 into summation of 1 to 6, 2x square plus 1. So this would just give you 1 by 6 into, you substitute numbers 1 to 6 in place of x. So 2 into x square plus 1, 3 plus, when x is equal to 2, 2 2s are 4, 4 2s are 8 plus 1, 9. And when x is equal to 3, 3 3s are 9, 9 2s are 18 plus 1, 19. So like in similar ways, you just substitute value up to 6 in place of x here. So when you solve for this, you'll get an answer. Let me just calculate that. Uh, 20. Yeah, so just calculating that, you get a value of 94 by 3. So that's the given answer. You should get some value like that. So yeah, so this would answer this question. Yeah, I see a lot of questions. So yeah, that's all about today's lecture and some of the examples we saw. I'll upload these notes now immediately. The YouTube video might take time. Like I might upload it tomorrow. Like that'll take some time. Mm, okay, I'm just reading the chat. Question number 1, question number 6. Oh, good. You have created your own groups. YouTube video, you cannot get it by tonight because, yeah, I'm sorry. I am in Australia, so it's already 12:30 a.m. here. So, yeah, it'll take some while to get processed from the cloud and download. So, yeah, I'll do it the first thing in the morning tomorrow, if that's okay. So, yeah, you should find the video when you wake up in the morning. Yeah, so it'll take at least an hour to process the whole thing. And that could be just too late for me because I have to leave for work in the morning. All right, thank you. All right, that's it about today's class. Yeah, I'll upload everything by like tomorrow morning. You'll find all the materials. And yeah, so if there's nothing else, we could end today's class. Okay, thank you all. Thank you for attending.